previous lecture, I defined the Schubert set corresponding to I, the element I. Next, we define Schubert variety. Corresponding to I. And we define also Schubert variety is depend on the reference track is defined by the closure of the Schubert set. And in fact, one can show that the Schubert varieties, in fact, given by it is not obvious by definition, but one can show that the Schubert varieties, in fact.
So this closure is topological closure.
Topological closure. In terms of usual topology or Zariski topology, but the same. For example, when I equal 1 to R, and the corresponding Schubert cell is represented by m times R matrix 1 0 0 0 1 0 0 1. Therefore, the corresponding Schubert cell consists of one point. If R is spanned by E1, E2, ER. So in this case, Schubert cell is 1 point. So the corresponding Schubert variety is also point. 1 point. Other extreme case is I is m minus r plus 1, m minus 1, m.
Dimension less than Q or greater than Q?
This is so P greater than P.
Greater than
Greater than P. Yes. Usually
the opposite is exactly equal to.
Equal, yes.
So the closure should be dimension.
Closure. Closure.本当
It's greater than.
greater than. Greater than. In this case, Schubert cell corresponding to represented by the following matrix: star 1 0 star 0 1 0 star 0 0 0 0 so the corresponding Schubert cell is isomorphic to CR n minus R. It is a this is called big cell. Note that the complex dimension Grassmannian is the same n minus. And the corresponding Schubert variety is the whole Grassmannian. This is the biggest cell. In the complex Grassmannian, we define the Schubert cell, Schubert variety as follows. However, when we wish to generalize these varieties to the general varieties, we think the Schubert variety as follows. For I1 EI is denoted by EI1, subspace spanned by EIR. And B consists of upper triangular matrices zero. Boyle subgroup. Then one can show that it is easy to see from this matrix representation of the cell. So xi Schubert cell is in fact B orbit. And Schubert variety is a B orbit closure of the B orbit. So when we wish to generalize these stories to the general Bragg variety G over P, G mod P, the Schubert cell is defined by the B orbit, and the Schubert variety is defined by B orbit closure of the B orbit. Yes, so far, I didn't mention the language of combinatorics. So now we introduce the language of partitions.
Excuse me, usually xi doesn't become a manifold.
Variety.
A variety.
But,
so is there any criterion of this becomes a manifold or not?
So, yes. There are some criterion whether the Schubert varieties are non-singular or singular. So, Sarah Billy and Shravan Kumar published singular loci of なんだかシューベルトバラエティスバックホイザー違ったバックホイザー In this book they discuss the singularities of the Schubert varieties and also Manivel's book he discusses singularities of Schubert varieties. So usually Schubert varieties singular varieties. As I mentioned earlier, we consider the partitions contained in the rectangle, the set of partitions contained in the R times N rectangle. N is M minus R. So we consider the partitions. And there is a one-to-one correspondence between this set of partitions and IRM. For each partition, lambda corresponds to I corresponding element is denoted by I lambda. I1, I2, I3. IP is defined by this sets up a one-to-one correspondence between these two sets. So, for a partition, lambda contained in R times n rectangle, we define the Schubert shell. Corresponding to lambda by Schubert series is usually denoted by omega lambda, which depends on the reference flag, is defined by x I lambda, circle. So more precisely, it is given by the following condition. N plus p minus lambda p k n plus p minus lambda p plus 1 most literature such as Fulton's Young tableau or Manuel's Schubert series defined by this condition. So by fact 2-7 omega Schubert series isomorphic to affine space Rn Rn minus weight of lambda and Grassmannian is Grassmannian as
less than minus
n plus p minus lambda p plus 1
minus 1 equal to don't you put minus 1 because
however
that's one I don't want to do the increase I want.
Using a jumping sequence, the condition is k equal p ip plus 1 minus 1 but
minus 1
ip is defined
that one so you don't
yes
minus
ip n plus p minus lambda p and is I n plus p plus 1 minus lambda p plus minus 1 so
yeah.
so yes so it is
right
yeah sometimes very confusing n plus p plus 1 minus yes so Grassmannian admits the following cell decomposition n r omega lambda marta and Schubert variety is defined by Schubert variety is corresponding lambda is defined by the closure of the Schubert cell. Closure. In other more precisely, dimension V cuts intersection n plus p minus lambda p is greater than p. This is definition of the Schubert variety. Then one can show the following facts. In fact, omega lambda is disjoint union of omega mu. It is not hard to show this fact. In particular, omega lambda contains omega mu if and only if. And also omega lambda is irreducible closed subvariety of Grassmannian, the Grassmannian of codimension, not dimension, codimension. Codimension is equal to the weight codimension is the weight of lambda.
That one's left-hand side is closed variety. Yeah.
Closed variety. Yes.
This one is
Open cell, but
you can do it.
but omega mu lambda, omega mu circle itself closed in the Grassmannian.
Sphere, think about circle. Circle can be consist of open line and point. Point is open. Point is an open.
This by one can show this fact from this definition. So.
Because mu is containing lambda, then it gives you more condition on this dimension restrictions here. So I think the implication is believable.
Yes. Xi, maybe it's easy to see xj mar using I, ij, irm.
Implication is
reverse. Yes. Natural natural lexicographic order. So we can show this. Then translate into the language of partition. For example, the Schubert cell corresponding to the rectangle. Rectangle is a point. And the Schubert variety is also a point. And Schubert cell corresponding to partition 0 is a big cell. And the closure is the whole Grassmannian. Let me give another example. When r equal 2 and n equal m equal 4, m equal to 4, so we consider the Grassmannian two-dimensional, two plane in C4. So there are partitions contained in the rectangle. 2 times 2 by 2 rectangle is given by 0, 1, 2, 1, 1, 2, 1, 2, 2. 0 partition corresponds to empty set. 1 corresponds to one box.
What was n? N was.
N was m minus r.
N minus.
Minus r. Two corresponds to 2 boxes. 1, 2. And the corresponding Schubert varieties are given by fix. F dot is reference frag consists of standard basis. Omega 1 two-dimensional subspace and dimension V intersection is greater than 1. We just write down this condition. So omega 2 is given by F1 is contained in V contains F1 and omega 1 is given by V is contained in F3. and omega to 1 is F1 V F3 omega 2 to is 1 point F2. So this is they are the Schubert varieties of G Grassmann 2-4. As I mentioned before, sometimes we think Grassmannian as a set of R minus one-dimensional subspace in P projective space M minus 1. So in this case, F1, F4, F4, F3, F2, F1, F0, and F3 correspond to P3 corresponds to hyperplane. Given line, line and point. So when we think of the Grassmannian as a set of Grassmann 2-4 as a set of line in P3, the Schubert series as follows. Grassmann 2-4 omega 1 is line in P3 which intersect omega 1 consists of lines in P3 which intersects L0, given L0, non-trivially. We defined this cell, this variety, L0. Omega 2 is line which contains the point P. And omega 1 line which contained in the hyperplane. Omega 2-1 consists of lines and omega 2-2 is given line. So please remember this Schubert cell. When we solve the question 1-1, which I mentioned in the first section, we will use this Schubert variety. So far we described the cell decomposition of the Grassmannian. Now we define the Schubert class. Section 2.4 Schubert classes. We are concerned with the cohomology of the Grassmannian, combinatorial aspects of the cohomology of the Grassmannian. So we define Schubert classes. Schubert variety.
Excuse me, this corresponds with the embedding of GR24 to...
Is
yes.
Sorry.
You said GR24 is a projective variety, so... So GR24 is a projective variety.
Yes,
there is some embedding to the projective
yes, P5. Purified embedding P5. Usually RM Projective の MR-1 So Grassmann の 2.4 is 4.2 minus 1から5.5
So this realization is there's nothing relation with this embedding. Yes. You give the Schubert variety. Schubert cells.
Schubert variety.
Is a subset in the P3.
Subset in
this case.
P3 in yes. V
But you are corresponding it to
P3 projective is
lines.
line sorry Grassmann の2.4をこうであって C4 で the dimension is 2 で also line であって
So L is you are already doing correspondence. You draw the correspondence.
こうですだから
You may consider this is P3.
こう
That's okay.
まあプリサイスに
Yeah, but in that case, you have already corresponded this with L0, which is already in P3, so it should be, I think previously it was okay.
So okay.
So the collection of lines in P3, that's
Yes.
collection of lines.
Collection of lines,
So
yes.
we just consider that as a P3. Oh, that's not in P3. Okay, I'm not an element, but contained in.
contain
Not an element, but just
そうこ
So it's not an element.
contained sorry I'm confused contained
So you make just the error contained in P3.
そうですそうcontain sorry で、Schubert variety corresponding to lambda, omega lambda is a closed subvariety of Grassmannian of codimension weight of lambda. So by the Poincare duality, each Schubert variety determine the cohomology class. Omega lambda defines cohomology class. But Schubert variety is in general singular variety. So we need some discussion about the definition of the cohomology class. For this account, see Fulton's Young Tableau book, Appendix B. We need some. We overcome some technical difficulties. Anyway, lambda defines a cohomology class, usually denoted by sigma lambda. This is a Schubert class. Corresponding to partition lambda.
Integer coefficient.
Integer coefficient. Cohomology is always integer coefficient. Remark. Schubert varieties depend on the reference flag. However, the Schubert class sigma lambda it is independent of the choice of the reference flag. This fact follows from the GLMC acts transitively. The set of all flags, and GLMC is connected, so it follows that sigma lambda is independent of the choice. But however, when we consider the equivariant cohomology, equivariant Schubert class depend on the reference flag. So be careful when you consider the equivariant Schubert class. However, in the ordinary cohomology, sigma lambda is independent of the choice of the reference flag. So.
When you corresponded this jumping number and this lambda, could you give me an example? It is, I have to memorize. It's confusing a little bit. the simple one, so that I can. So you have lambda,
lambda.
this partition, and
Partition.
you have jumping number.
Jumping
So from jumping number, how do you get partition?
There's a convenient way
Yeah.
to translate one such.
So you translated everything into this partition, right?
Yes,
You
yes.
did it in the jumping number.
Yes, jumping up. So the set of partitions, set of partitions contained in rectangle, and one corresponds I R n lambda R I IP is n plus p minus lambda p equal. So using Young diagram, the relation it is easy to describe the correspondence. For example, when R 5 7 N 7 7 lambda 4 for example and you start northeast side. We start line. We put number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then the corresponding I is 4, 6, 7, 10, 12. Ah, 4, 3, 0. Okay. 5. So using Young diagram, the vertical, the number appears on the vertical line is the corresponding I. So we always translate a partition and jumping sequence using the diagram, Young diagram.
This n is m minus r, right?
Yes, n is in this case m minus r. So m so we are considering Grassmann 5. So, we give the cell decomposition of the Grassmannian by Schubert cells. From this, we obtain the following basis cell. The cohomology of the complex Grassmannian is free Z module generated by Schubert classes. Free Z module generated by sigma. And we refer to sigma lambda as the Schubert basis. So in the context of the Schubert calculus, the additive structure of the cohomology is completely described. So, the additive structure. Grassmannian is completely described. In terms of Schubert classes. This is the additive structure of the cohomology of the Grassmannian. And the remark the situations are very quite analogous for the equivariant cohomology or quantum cohomology. And I want to mention a little bit a few about equivariant cohomology. T denotes the maximal torus. Borel subgroup contains the Borel subgroup. Maximal torus. C star. In this case, we can define the Schubert variety. In fact, this Schubert variety is omega lambda is T invariant. So this Schubert variety defines cohomology class. So in this situation, T equivalent cohomology of Grassmannian is additively
So this parent group is acting on a flag,
Yes.
reference flag.
reference flag. Yes, yes. で、そうですね。レファレンスフラグです。In this case, additively, the equivalent T equivalent cohomology is generated by Schubert classes, parameterized by the partitions contained in the rectangle. The sigma lambda T equivariant Schubert class, and S denotes HT star point. T equivalent cohomology ring over point. So the cohomology ring of the Grassmannian space of T BT polynomial ring. T っていうのかな、ポリノミアル。Additively, T equivalent cohomology S module, free S module generated by Schubert classes. And in this case, T fixed point is a finite set and also parameterized by partitions. Fixed point is fixed point set inclusion. The induced map in cohomology, induced homology, so-called localization map. The right-hand side, since the fixed point set is finite set, so it becomes polynomial ring, direct sum of polynomial ring. T polynomial, direct sum of polynomial ring. And I don't know much about GKM theory, but GKM theory asserts that this localization map is injective. So we think the equivalent cohomology as a subring of this direct sum of S. So one of the main interests of this description is the image of the Schubert class. What is the image of the Schubert class? We denote each factor, the image of each factor. We denote mu. So each equivalent Schubert class corresponds to the family of polynomials. So in fact, this polynomial is so-called factorial Schubert polynomial. we can give the T equivalent cohomology of Grassmannian as we can give the combinatorial description of the T equivalent cohomology of Grassmannian.